That's why my computer's been working so well. I should have known. I should have known something was up when things weren't glitching the whole time. So we're going to do a table of values, but for that blue function. So y equals negative 1 over 2x squared. To see what the y value would be, you just put negative 2 in for x. Negative 2 squared is 4. Right? 4 times 1 over 2 would be 2. So my y value would be 2. I'm going to draw that. So that would be a point at negative 2 and 2. There's a point right there on my new graph. Negative 2, 2. Let's do another one. Oh, I probably should have gone out to negative.
Wait, how did we get minus 2 for x?
I'm just choosing numbers.
Oh.
Yeah. We should go to negative 4. See, Michelle's smarter than me. I should have just listened to her. Just a sec. I'm going to do the first one. Negative 4, negative 3, negative 2, and 2, which we know. Negative 1, 0, 1, 2, 3, 4. Miss Schaub's smarter than I am. You know, I just should just trust the woman. Okay, so getting these points. Put negative 4 into this equation. Negative 4 squared becomes positive 16. Positive 16 times 1/2 would be 8. So that means I have negative 4 and 8 is one of my points on my new graph. Look at that over here. Draw a dot at negative 4 and 8. Next one is negative 3. Negative 3 squared is 9. Positive 9 times 1 over 2 is going to be 4.5. So negative 3 and 4.5. Negative 1 squared is 1. 1 times 1 over 2 is 0.5. So I have a point right here at negative 1 and 0.5. Zero squared is 0 times 1 over 2 is 0. 0 stays at 0, 0. One would turn into, well, I was just going to start putting answers, but that I got to verbalize it. So 1 squared is 1 times 1 over 2 is 0.5. So draw a dot right there. 2 will be at 2. 3 will be at 4.5. And 4 will be at 8. So you can draw your dots. 4 and 8. Like that. And you can kind of connect the dots so you can see what this looks like. I'm going to try my best. It is a quadratic function, so you should have a nice little curve. You've got lots of points to connect here, so it should look pretty smooth. Looks like that. And it does have arrows on the end because it does keep going, right? It goes forever. Fantastic. So we got these two graphs. We got y equals x squared, just this basic black one. And then we got y equals 1 over 2x squared, that blue one that we just drew together. Let's answer some questions about these graphs. And then how have these graphs actually changed? Like what's actually happened here? First, let's talk about a term that you should have remembered from last year. It's called invariant points. What's an invariant point? Throw back to Math 20-1.
I believe this is the point where both of the graphs intersect.
Yeah, invariant, like variant would be changing, yes? Invariant would be not changing. So you're talking about points that don't change. Points that are on both things, both graphs. There's one right here. It's at 0, 0. That point is on both. It did not change. And it is the only spot that's on both. Those lines never cross each other again anywhere else. All right, so that is the only invariant point. It is at 0, 0. That's my only invariant point. Cool. How's the graph transformed? So what's actually happened here? To see how something's transformed for this one, I like to take points from the original graph and try to figure out where that point has now gone. So if I look at the original black graph, there's a point up here. That point is at -4, 16. If I look at my blue graph and I look for where x equals -4, I get this point. That point is at -4, 8. X values stayed the same, but the y values have changed. It went from 16 to 8, divided by 2. If we keep checking points, you're going to keep seeing that happen over and over again. Look at this point right here. I'll do it in purple, green. This point is at 3, 9. Sorry, -3, 9. If I look on the blue graph, that's -3, 4.5. The y value went from 9 to half of 9, which is 4.5. And you can do that for every single point on this original graph. And you will find that what's happened is the y values have all been cut in half. I say divided by 2 because that's like logically makes sense to me. Right? 9 divided by 2 is 4.5. Is good? Yeah. No. I think I want to leave. But technically, it's actually been multiplied. It's not been divided by 2. It's been multiplied by 1/2. And it's been multiplied by a fraction. It's the same effect. Okay, I always talk about it as division because logically in my brain, that makes sense. It divided by 2. But dividing by 2 and multiplying by 1/2 is the same thing. Okay, so that's the terminology we will have to get comfortable with, is that we multiplied. We didn't just divide. So that question in the bottom left corner, how is this graph transformed? It is transformed. The y values have been multiplied by a factor of 1/2. That's not perfect mathematical terminology, but it's good for us just to understand what's going on. Okay, so it was multiplied by 1/2. Cool. Let's look at this one. So you have a graph there. This one is x squared minus 10. The dots are not connected for you there. No, they're not. Okay, so we'll connect them. Looks like this. Oh, I missed a little bit there. That's okay. That's our original graph, x squared minus 10. Now they've changed that graph. They've changed it to be 2x squared minus 10. Notice that the effect is inside the brackets. That means that 2 is actually being squared. Right? Whereas the last question, it was outside the brackets. There was no brackets there. Subtle difference. Let's do a table of values again so that we can kind of plot where these new points are. So if I had x equals -4, see, that's not what I want to do. No, that's going to be too far off the chart. Hey, that's going to be too far. I'm just going to do a couple here. Let's do -2, -1, 0, 1, and 2. That'll do the trick for us. If you put -2 into your new function right here, -2 times 2 is -4. -4 squared is 16. 16 minus 10 is 6. My first point is at -2, 6. Right there. Next one, -1. So you put -1 times 2 is -2. Squared is 4 minus 10. Oh, I went too fast in my own head. -6. So -1, -6 right here. Zero times 2 is 0. 0 squared is 0 minus 10. I have 0 and -10 right here. One times 2 is 2. 2 squared is 4 minus 10 is going to be -6 again, and then +6 again. So my new blue graph should look like this. We connect our dots, making a nice quadratic. That is not a nice quadratic, but that's the best I can do right now. A little pointy and a little wavy on the right. Perfect. My black graph has transformed to that blue graph. I see people still writing dots, so I'll give you a minute just to get those dots down. Are the invariant points on those graphs? Invariant points that didn't change. 0 and -10 did not change. Right down here. Invariant points down here at 0, -10. That point is on both graphs. It did not move. Perfect. Describing how this graph has transformed. These ones I find trickier to demonstrate on what's actually happened. So the way I'm going to show it is if I look at a point like this. That point is at -2, -6. I notice that right next to it is another point from the new graph. The y values are the same, but that one is now -1, -6. The x value has divided by 2 there. If I look at another one, let's do, did I do -2? Yeah, at this point, it's not on the original graph, is it?
Yeah, it is. I think your arrow says it.
Is it right here?
Mm-hmm.
Oh, there it is. I'm like, it didn't draw it. There we go. That one on the left, on the original, is at -4 and 6. If I look to the right, I see a new red dot. It's now at -2 and 6. And we can start to kind of draw a conclusion that the x values are now being affected. But they're not multiplying by 2 like you kind of would think. So if you look at the function, you would almost think the x values are doubling, multiplying by 2. They didn't. The original function was 4. The new function is -2. So it's actually dividing by 2. That's how this graph has transformed. The x values were dividing by 2. Instead of saying divide, though, we're going to say it multiplied by a factor of 1/2. Right? Same idea. Dividing by 2 is the same thing as multiplying by a half. So how is the graph transformed? The x values are multiplied.
Why do you always multiply?
Yeah, I was gonna ask.
That's a good question. That's just how they always discuss it. Why do they always talk about it through multiplication of factors? Why wouldn't they? Because to me, it makes more sense to say it's divided by 2. Like, that's how I would discuss it.
Does it make a difference on the test?
It does. You would say it's multiplied, and that's why I'm saying it. My guess is because we've always been dividing. Like, our 2 graphs, our 2 examples so far are dividing. But we will have graphs that stretch and get bigger, and they do get multiplied. So then you would have to be saying divided by to keep things consistent. I think that's probably why they use the word multiply, just so it's always multiplication when we talk about stretches. But I agree, like logically, it's divided. You know what I mean? Like I look at that, and I'm like, that divided by 2. All right, so I get that that's kind of a pain in the butt. But the x values are multiplied. Yeah.
Is there like a proper mathematical way to say it? Like, would you say like it's horizontally stretched
Yeah.
by a, okay.
Yeah, we're going to get there. The x values are multiplied by a factor of 1/2. That's a period, not a circle. And we will get to like the proper terminology. So again, like that's not properly mathematically written. We will edit it a little bit to make it sound perfect for a diploma test and for an exam. But just speaking about what's happening, that's what's happening. The x values are all getting multiplied by 1/2. So any dot on the original graph, you could find the new dot by just taking the x value, multiplying by 1/2, and sliding it inwards. Awesome. Here's the proper mathematical terminology for you. So what we've been doing is we've been stretching our graphs. Okay. When we were changing the y values, we call that vertically stretching something. Y values is vertical, right? So you vertically stretch something. When we were multiplying the x values, that's called a horizontal stretch. Horizontal is x values, so you're moving it in and out like this. Okay, that's what we were doing. In function notation, it looks like this. That's the function notation of it. You have y equals a f of bx. The a is the vertical stretch. That means it's happening to the y values on your graphs. The b represents your horizontal stretch. That's not good. There we go. So I got A, my vertical stretch. I got B, my horizontal stretch. Perfect. Proper terminology. Instead of saying it's vertically stretched by a factor of what, you technically have to say, or instead of saying multiply by a factor of what, you have to say that it was vertically stretched by a factor of whatever, and you have to say what you were stretching it from. Okay, there's got to be like a reference point at which you're stretching something away from. What we're stretching it away from was the axes. So when you look back at these graphs, what I was doing was I was taking this point and I was stretching it closer or further away from the y-axis. With the other one, what I was doing is I was stretching it further or closer from the x-axis. Right? So if I took a y value and I multiplied it, then I'm stretching it away from this x-axis, or technically closer to the x-axis. When doing stretches, you do have to mention that. And that's where like the proper math terminology that I keep talking about comes in. So it says the function is vertically stretched. Vertically stretched is a keyword by a factor of a. So you'd say what the factor is. And then you have to say about the x-axis. That means you're stretching it away from the x-axis.
What if it wasn't an axis?
For now, it'll always be from the axes because it will just always do the y and the x values. So it keeps it pretty straightforward. At one point, we do talk about somewhere else. So it will come. The reason why is because technically you could stretch it away from something else. Like you could put a new line and be like, stretch it from that point. We just don't see a lot.
Like if x is like 6.
Yeah.
You can also stretch it like toward the x-axis. Can you stretch it like in?
Yeah, and like, so remember when we said we were dividing by 2?
Yeah, and you would multiply.
Then technically we were multiplying by 1/2, and it was getting closer to the x-axis. But that still counts as stretching about that axis. So that terminology will never change. You will always say by a factor of the x-axis. Like that's not going to change for you. Even if it was getting closer, we call it a stretch. The other terminology would be you're horizontally stretching. Horizontally stretching. So that's when we're multiplying the x values by a factor of 1 over b. So remember how we had 2x, and then we actually realized it was 1 over 2? It wasn't doubling, it was dividing. So your horizontal b values is actually 1 over b. And that is about the y-axis. You are stretching away from the y-axis. Or technically closer, if you were like squishing it inwards. Yeah. Yeah. Yes. So if we look at a picture like this one, we took our x values and we were stretching them closer to the y-axis. See how it moved inwards? It came closer. It came closer. Right? That's stretching about the y-axis. So it's getting closer to the y-axis.
So what it says that invariant points are always on the axis of stretch. So if your invariant point is on like the y-axis, does that mean it's horizontal?
Yeah, as long as it's not the origin. So it's not on both axes, like because that screws things up, right? Like you see them as right here, then it's on both axes. But yeah, so what Emily's asking you is when you see the invariant point, does that tell you the type of stretch you have? For sure it does. My invariant point was right here on the y-axis. That's because I was stretching closer or further away from the y-axis. You can't stretch further away if you're already on the axis. You can't stretch closer if you're already on the axis. You're stuck there.
How would you do it the other way?
So if you look at this graph.
So if it's getting flatter or wider, it's...
Like this one didn't move because I was stretching away from the x-axis. Right? So it was stuck here because it was already on the x-axis. 0 times anything is going to be stuck there. It won't move. It's weird, right? Stretches are significantly harder than translations. Let's look at some examples because then you'll see the terminology and we can talk about it a little bit more, which helps. So let's look at these examples. It says the function f of x is transformed. Determine the equation of the transform function. So we're just doing function notation. I'm going to add a little bit to the sentences because it's missing something in some of them. Okay, so you have a vertical stretch by a factor of 6. And then it should technically say like about something. So if it was a vertical stretch, it'd be about the x-axis. So what's happening here? Vertical stretch means I'm taking something and I'm like pulling it upwards, right? Like I'm stretching it vertically. By a factor of 6, that means I'm taking every point and I'm multiplying by 6 to go higher. And I'm stretching away from the x-axis. Okay, so it means if the x-axis is here, I'm getting further away from it. I'm either going up or down away from it. In function notation, vertical stretches is the a value. This would look like this. Y equals 6 f of x. That is vertically stretched by a factor of 6 about the x-axis. That's the function notation for it. Let's look at B. Again, I'm going to have to add about into there. A horizontal stretch. That means I'm taking things and I'm stretching them sideways. Right? The x values are changing by a factor of 1/3. And then it says about the y-axis. It should say that, right? It should have that terminology in there just so we're used to it. That means I'm stretching away from the y-axis at a rate of 1/3. All right, in function notation, what does that look like? So in function notation, horizontal stretches is telling you the b value. But it's a little messy. Remember with like our x values when we were translating, it would be like -3, but it actually meant 3. It was going to the right. Horizontal stretches also do that same kind of weird thing. So when you're talking horizontal stretches, if the factor was 1/3, that meant that the b value was actually 3. It was not 1/3. So my function notation looks like this. Y equals f of 3x. Something I do to help me is now you start to get into this like weird situation where it's like sometimes the number actually matches, sometimes it's like the opposite of what it looks like. When you're talking about vertical things, so translations, vertical translations, or stretches, vertical stretches, the value is actually the value in function notation. It's like straight up, it's telling you the truth. So when I say vertical stretch by 6, the number 6 is actually in my function notation. When you're talking horizontal anything, so horizontal stretching, horizontal translating, so it's shifting, then it's going to be the opposite, right? So our horizontal translations would always be minus something. And our horizontal stretches, the factor actually is the opposite. So instead of 1/3, it's just 3. It reverses. It's weird. Yeah, it has to do with like the math of when you put it into a function, what's actually happening. So by tripling the x value, it actually makes the y value change in a different way than it looks. Let's do another one. So you have a stretch about the y-axis by a factor of 5/2. Okay, so if I'm stretching away from the y-axis, that means I'm stretching horizontally. So this should be called a horizontal stretch. I know it's horizontal because I'm stretching away from the y-axis. I'm going sideways. I'm going away from the y-axis by a factor of 5/2. Okay, so because it's horizontal stretch, I'm talking about the b value. But the b value is not 5/2. It's opposite of how it looks. So the b value is actually 2/5. Meaning that my function notation looks like this. Y equals f 2/5x.
If it's a vertical stretch, do we do it the right way?
Yes. Anything vertical stays like true to itself. Like what you see is what goes into the function notation. Anything horizontal is switching. Easily like one of the most confusing things that I think we see. I truly mean that. Like you could ask me in a week about transformations and I'll still mix it up in my head. Because it's so easy to just be like, wait, is X value opposite? Or, it's easy to just flip in your head. D, a stretch about the x-axis. Okay, so if you imagine you have an x-axis, you're stretching away from it. That means we're talking vertical. Right? This will be a vertical stretch about the x-axis by a factor of 1/3. That is a vertical stretch. I know it's vertical because I went away from the x-axis. Vertical stretches are talking about my A value. Because it's vertical, that means A actually is 1/3. And there's another stretch. A stretch about the y-axis. So if I think about it, I have my y-axis. I'm getting away from the y-axis. That means I'm going horizontally, right? I'm stretching side to side. This is a horizontal stretch. About the y-axis by a factor of 1/10. Because it's horizontal, that means we're talking about our B value. But it's not B equals 1/10. This would be B equals 10. My equation would be y equals 1/3 f of 10x. Like that. There's my A, my vertical stretch. There's my B, my horizontal stretch. The vertical one stayed true. The horizontal one flipped. Everything horizontal is the opposite of how it looks. Mine's being blown. Yeah. You would have seen these things in Math 1. We did stretches and transformations of quadratics, but we basically focused on vertical stretches. We didn't do too many horizontal stretches. A little bit, not really. All right. Let's try a question. Practice problem says plot the points A, B, and C after a stretch about the line x equals 0 by a factor of 1.5. Okay, so you got 3 points there. Point A, B, and C. We are going to stretch them about the line x equals 0. Where is x equals 0?
Y-axis.
That is the y-axis. All right, x equals 0 is the y-axis. I did this and said y-axis. Y-axis. Perfect. By a factor of 1.5. That means you want to multiply by 1.5. And because you're going horizontally, which values are we going to be multiplying by 1.5? The x or the y values? Half people said x, half people said y. That is a sign that this is spot on and we're good to go. You guys ready for a test tomorrow? Yeah, so if you're stretching away from the y-axis, give me a second here. I'm going to draw. There's my y-axis. There's my y-axis, agreed? I want to move away from that y-axis, left or right. Right? If I moved up or down, I'm not getting any further away from the y-axis. I need to move left or right because I'm stretching away from them. So if you're moving left and right, which values are changing? The x values would change because you're going left or right. You're moving your point away from the y-axis. So the x values are changing. Okay, I'm actually going to write that down. So when we saw that it was about the y-axis, that tells me that it is going to be a horizontal stretch. Right? I'm moving away from the y-axis. Horizontal stretch affects what? Is it? That's good. Did it pop up? Yeah. Good. Horizontal stretch affects x values. It's horizontal. X values are horizontal, left, right. Before I actually do any stretching here, how do we feel about stretching about the y-axis is horizontal? Feeling like, all right? What a day, hey? Want me to call Michelle right now? Who all wants to drop? The looks in your face is you're not allowed to drop. So even if you want to, you're not allowed. That's what you think. You're trapped now. Yeah, you're trapped now. You're stuck here with me. Okay. Oh, okay, that's a good question. Okay, so why am I talking about the y-axis when I'm talking about x equals 0? That's a good point. The y-axis is all of the points in which your x value is 0. So if you went to any point on here, this would be 0, 6, right? X would be 0. You go here, this would be 0, 10. X would be 0. That's why when I'm saying x equals 0, I'm talking about the y-axis. Because it's all the points in which x is 0.
Oh, that makes sense.
Yeah, okay, that helps probably a little bit. Well, I'm like, why are we talking about y-axes? Okay, so when it said x equals 0, the reason that y-axis is because these are all the spots where there's an x value of 0.
Okay.
The y is changing, but the x is always 0. Yeah.
Well, I was just thinking about this. So we're stretching everything by a factor of 1.5, right?
Yep.
So considering it's a horizontal stretch, it goes inside the brackets with the x, right?
Yep.
So put that into function notation. 1.5 is 3 over 2.
Yep.
You have y equals f 3 over 2x.
Yes.
Right? So, but you said that the horizontals flip. And so if you have that, it'd be y equals f of 2 over 3x, which means that you get closer to the y.
Yes. Okay. So he brings up a good question because he's now talking about function notation. Okay, so there's two things that are important here. There's function notation, and then there's like the sentence, which says by a factor of. When it says by a factor of, that's what you actually multiply to your values. So in function notation, that value is not what you multiply by. It's the factor of in which you multiply. So to do this stretch, because we haven't stretched anything yet, you're going to go to the points. You're going to take a point that is currently at -4, 3. You are going to multiply the x value by 1.5. So that means this point would now be -6, 3. And notice how it has stretched away from the y-axis. Now, in function notation, it would not be 1.5x, and that's what you're getting. It wouldn't be 3 over 2x. It'd be 2 over 3x. We just haven't linked that together yet. But it's the phrase and the sentence, that's the value you multiply by.
So then if it didn't have that phrase, would you do the normal flip?
Then you'd flip it and multiply by that flip value.
So how would it ask for that without using that phrase? Like, would that ever happen?
It will happen. We still stop back. We still got a couple minutes here. Like 1 minute. You could do this exact same question and say it's stretched by this new equation. And then you would have to know to change that into a sentence of 1.5. Yeah. I'm going to put the last 2 answers up there so that you have them in your notes, and then we'll do the next questions tomorrow. This point would go to here.